Hello viewers, welcome you all. So well, in this lecture, I am going to take up some important topics of digital electronics, right? I will take up only those topics which are easily to understand and important from the point of view of examination. Because I am keeping in mind that this course, digital electronics course, is not included in the syllabus of UG level teachings or UG level programs in Himachal Pradesh University, right? So I'm keeping it in mind. So I'm not touching all the things. I'm only just considering important points which can be understood in an easy way, and from where question can be asked, right? So first of all, I'm starting with basic logic gates, right? So logic gates, although you have studied about the logic gates in your 12th class also, but I'm recalling all these things once again, then I will proceed further. So logic gates are basically electronic circuits, right, where the output follow a certain logical relations between the inputs, right? Inputs can be one or more than one, right? And in case of logic gates, the output follow a Boolean logic, right? Boolean basically it is the name given to the logic or algebra developed by English mathematician George Boole, right? George Boole. He has developed a logic that is known as Boolean logic, and that equations are known as Boolean algebra, right? So these logic gates, they follow the logic of Boolean, right? And we call that call these circuits as logic gates, right? So we have some basic logic gates. So I'm telling you about the basic logic gates. So these basic logic gates are OR, AND, and NOT. These three gates are the basic logic gates, right? Now you have studied about the in details. OR means output Y is equal to, if we are considering two inputs, then Y is equal to A plus B. Here plus is according to the Boolean logic. Similarly, AND Y is equal to A and B. NOT means Y is equal to A not, only one input, right? Here we can have two or more than two inputs, same here, but NOT gate has only one input, and the output is the inversion of that input, right? So these are three basic logic gates, right? We know what is the output equation according to the Boolean logic for these gates, right? Now, usually examiner can ask you the corresponding circuit to realize these basic logic gates. How I can realize a OR gate or AND gate or NOT gate by using circuit elements. As I told you that these gates are basically electronic circuits, right? So if I want to realize a AND gate, then I can realize a AND gate. You can see here by taking a diode, right? This is PN junction diode, right? I must have two PN junction diodes connected in this way. This is the resistance. This is the supply 5 volt. This is for output Y, and this is for input A and B. So this is the very simple circuit that can be used. This is diode D1, this is diode D2. This is the very simple circuit. This is resistance R that is used for designing a AND gate, because this circuit output Y will follow this relation, right, for this circuit. And you have undergone the working of this circuit in your 12th class. You have understood all these things, how this circuit works, but you have to remember this is the basic circuit that is responsible for this AND operation, right? Similarly, if I want to design a OR gate, right, this one, then how I can design it? I can design it again by taking two PN junction diodes. this one, and then you have this is the output by, this is input A and this is input B, right? So this is diode D1, this is diode D2, right? This is virtual ground and this is resistance R. So this is the circuit, basic circuit that do the OR operation, right? This one. But we need two PN junction diodes, a resistance only, right? But in this case we need two PN junction diode, a resistance and a supply voltage, right? Now if I want to construct NOT gate, very important, then for constructing even I can design this circuit by using transistors, right? But this is the basic or very simple way of designing circuit by using PN junction diode. If you use the transistors, then circuit will become a bit complex, right? Similarly, the very basic circuit that is used for or NOT operation, that is a, this is not proper circuit. Yes. Now this is a transistor, right? This is emitter of the transistor, right? This is base R1, right? And this is the input A, right? Similarly, I have here, this is the output by, this is plus 5 volt, and here ammeter is connected to the virtual ground. So this is the basic circuit that is doing, this is resistance R2. This is going to do the operation NOT, right? NOT operation. NOT means y is equal to A NOT. Here AND means y is equal to A and B. And here OR means y is equal to A plus B. So these are the three basic logic gates and their corresponding basic circuits, right? We have to remember these basic circuits, very important, because as far as truth table or this Boolean logic equation is concerned, all of you know them very well, right? But this thing is important from the point of view of exam, right? Now you know very well we have some additional logic gates, right, that are constructed by using these three basic logic gates. So they are like NOR gate, right, NAND gate, right, XOR gate, right, XNOR gate. All these gates are constructed by using these basic gates. For example, NOR gate. NOR means OR plus NOT, right? And you can write y is equal to A plus B NOT. This is the logic equation. Similarly, NAND means AND plus NOT, right? NAND, that will give you y is equal to A and B NOT. XOR. Now for constructing a XOR gate, it is very important. You need more than two components. You need two AND gate, right, plus two NOT gate at least, plus one OR gate. Total 5 components minimum required for constructing a XOR gate. We also call it as exclusive OR gate. Then you will get the expression y is equal to A naught B plus A B naught. This is the Boolean logic expression, right? If I come across XNOR, XNOR means we are going to connect NOT gate with XOR, right? XOR plus NOT, that will give me XNOR gate, right? So one more component is added, that is NOT gate, right? So that will give me y is equal to A naught B plus A B naught whole term this. This is the Boolean expression or Boolean logic for this XNOR gate, right? As far as the circuit symbols are concerned, we know for NOR gate, we have to remember, the logic symbols for them, all of them, like OR gate. OR gate, this is OR gate, you know very well, for two inputs. AND gate, right? NOT gate. So these are the basic symbols, right, for these basic gates, right? So these are the symbols. Now, as far as NOR gate is concerned, NOR means OR plus NOT. So NOT means bubble here on the output. This is NOR, right? NAND means and bubble NOT. This is NAND, right? What is XOR? XOR means, as I told you, it is a combination of 5 different logic gates XOR, right? This one, this is XOR. And if I go to the XNOR, NOT and XOR, right? So these are the circuit symbols that we have to remember for all these gates, right? Now, out of all these gates that I discussed here, 3 basic gates and then these gates, uh, which of these are known as universal gates? I mean, any gate can be constructed by using that gate. So universal gates are NAND gate and NOR gate. These 2 gates are known as universal gates. We can construct any of the gates by using these 2, right? Separately, I can use NAND gate, only NAND gate, right? I mean, more than one NAND gates will be used, right? Or one NAND gate can be used for constructing not like that. So similarly, for NOR gate can be used for constructing any of the gate. That's why we are calling them as universal gates. So you can be asked that given a circuit that by using NAND gate, how we can design AND gate, OR gate, NOR gate, or even XOR gate, right? So you have to simplify then according to this Boolean logic equations, right? So these are universal gates, right? So this is about the basic logic gates, and then some additional gates, universal logic gates. Now I am coming to one of the important topic here in this uh, logic gates, that is the simplification of Boolean expressions. Simplification of Boolean expressions. Boolean expression means you will be given a expression in Boolean logic like y is equal to a not b plus a b plus a b not plus a b not, like that, and you will be asked to simplify this Boolean equation or expression and then draw the corresponding circuit. You can see here, I can even draw this circuit by using different gates, but the circuit will be more complex. So I can simplify this equation by using some Boolean laws, and then after, the requirement of the circuit element will be reduced. You can see, I will take up some examples. So this question is usually asked, right? Simplification of a Boolean expression. You will be given expression, you will be asked to simplify this Boolean expression, and options will be given, or otherwise you can be given a question and you will be asked to draw the corresponding circuit, right? Logic circuit. So in that logic circuit, first of all you have to simplify the expression. Now to do it, we need some laws for it. So starting with the first 2 laws or theorems that are very, very important, that theorems are De Morgan's theorems. De Morgan's first theorem or first law, and De Morgan's second. Yep. Right. So I am taking up these 2 theorems, De Morgan's first and second theorem, right? So according to De Morgan's first theorem, NOR gate A plus B. NOR gate is equal to bubbled AND gate. A and B and bubbled, right? So this means that these two circuits are equivalent. NOR gate means if I draw the circuit of NOR gate symbol, this is NOR gate. So I can say this circuit is exactly equivalent to bubbled AND gate. Bubbled AND, this is AND, right? Bubbled means two inputs are inverted before applying the AND operation. So according to De Morgan's first theorem, NOR gate is equal to bubbled AND gate. You can explain it with the help of truth tables, right? So this is De Morgan's first theorem. We have to remember the statement as well as this, right? Equivalence of these two logic circuits. Similarly, De Morgan's second theorem link the NAND gate. NAND, A and B. NAND gate is equal to equivalent. I will say equivalent to the bubbled OR gate. A plus B, same thing, but now the Boolean logic is reversed. NAND gate is equal to bubbled OR gate. So NAND gate, this is NAND, right? That is equivalent to the bubbled OR gate. This is OR gate, right? Bubbled means two inputs are inverted before applying the OR operation. So these two theorems you have to remember. De Morgan's first theorem, this is the first theorem. Don't write this as the first theorem. These are already defined. De Morgan's first theorem or first law and the second theorem. So we have to remember, according to De Morgan's first theorem, NOR gate is equal to bubbled AND gate, and according to second theorem, NAND gate is equal to bubbled OR gate. So before proceeding for the simplification of Boolean expressions, we have to understand these two basic theorems of this digital electronics. Now we have some additional laws, right? Like I am writing them all one by one. First is when you add A plus 1, that will always give you 1. Why? Because if A is 0, then it is 1, right? 0 plus 1 1, it is 1 plus 1 1, right? If you write A into 1 AND operation, you will take, it will give you A, right? If A is you can see, if A is 1, then 1 into 1 means A. If it is 0, then it will become 0. So A into 1 is equal to A. This is the second law. Similarly, third one, right? A plus A, that will give you A, right? Similarly, A into A, that will again give you A, right? A plus B, that will give you B plus A. They are equivalent. Similarly, A into B, that is equivalent to the B into A, right? Similarly, A plus A bar, it is always equal to 1, but A dot A bar, right, it is always equal to 0, right? You can see here, right? So these are some important laws. That one I forget, I think, that is A plus B plus C is equal to A plus B plus C is also there, right? There are a few more that I am adding here, 10, that is A into B plus C, that will give you A, B plus A, C. Similarly, 11th, A plus 0, that will always give you A, but A into 0, that will always give you 0, right? A double bar, not double not, it is always equal to A, right? Similarly, if you have A plus A, B, that will give you A, but it is, I think, simplified using this, because they have taken A as common, so it will give 1 plus B, so 1 plus B is always 1, so A into 1 A. So the you have to remember all these Boolean laws and to De Morgan's theorem in order to simplify any Boolean expression, right? I am taking a few examples, right? you will be given an example that draw the corresponding circuit for the given Boolean expression. Question number 1, y is equal to a b bar c plus a b c. Now if you look at this expression, then this expression can be simplified. Otherwise it looks that you require 3 inputs. But let's see how it will be simplified. A and C are common. A, C, we are left with B bar plus B. So B bar plus B, you look at here, where it is? Yes, this one. It is A plus A bar means B plus the same thing, 1. So AC into 1 means AC. So it means Y is equal to A into C. So what I need? I need only a AND gate, right? Otherwise, if you look at this, you need AND gates plus a OR gate, right? 2 AND gates plus a OR gate. So only one AND gate is needed, that is going to solve the purpose of this equation. This is how this equation is simplified. I am taking one more example. You have a equation y is equal to a bar, b bar, c bar plus a bar, b, c bar plus a, b bar, c bar, bar means not, plus a, b, c bar. Now if you look at this equation, you will find that this is complex equation. It needs at least 4 AND gates plus 4 AND gates plus OR gate, right? But let's try to simplify it, right? So C bar is common in all 4 terms, so it gives me A bar, B bar plus A bar, B plus A, B bar plus A, B into C bar, right? Then I am further taking some common things here. So A bar, right, is common in both, so it is B bar plus B, right? Then A is common, A, B bar plus B and C bar. Now B bar plus B, 1, 1, so A bar into 1 A bar plus A into 1 A into C bar. So when you will simplify A bar plus A 1, so Y is equal to C bar. So you can see how this large expression is simplified, and it is giving us Y is equal to C naught. Only we need a NOT gate to draw the corresponding circuits. So this is how a question is asked from these Boolean logic expressions or Boolean equations for the simplification. So this is actually an important topic, so that's why I have covered it. So you have to remember 2 De Morgan's theorems and these some laws in order to solve these expressions and then to draw the corresponding logic circuit. And these were some basic logic gates. So I am hopeful that I have explained these basic things of digital electronics. So thank you very much.